Okay, the final lesson of this week is secant angles. I sure do hope someone's watching these videos. They take me a long time to make. Alright, we've talked so far about central angles. We have our central angles here. A central angle is an angle that comes out of the center. The vertex is in the center. Whatever the angle is of the central angle, the intercepted arc is the same degrees. So this is 60 degrees, intercepted arc is 60 degrees. Then we come over here to inscribed angles. An inscribed angle, the vertex, this is the vertex. We often name the angle, like if we put an A here, we can call this angle A. The vertex names the angle. If you have an inscribed angle, the vertex is on the circle, and it goes through the circle. So if the inscribed angle, angle A, is 60, the arc that it intercepts is twice as big. So the intercepted arc here is 120. And you can go the other way. If you know the intercepted arc, you can find the angle by dividing it in half. So those are the two things we covered so far. We talked a little bit about chords and things like that. Now we're going to move on to what's called secant angles and secant lines. We'll do the tangent line too. A tangent line, remember, is perpendicular to the radius. A secant line is just a line that intersects a circle in 2 points. So right here, this green line, this is a secant line. It intersects the circle in 2 points. A tangent line intersects the circle at only 1 point and is perpendicular to the radius. So a secant line is 2 points. A secant angle is an angle whose sides are contained in the two secants of the circle so that each side intersects the circle in at least 1 point other than the angle's vertex. So this is just one example of a secant angle. These actually all are secant angles. Right here's a secant angle, here's a secant angle, here's a secant angle, and here's a secant angle. So it's just when two lines intersect somewhere in the circle by secant. These are both secant lines and they intersect. Actually, secant lines can also intersect outside of the circle, and there's still a secant angle, which we're going to get to in a minute. Alright, let's talk about the two theorems that are in this chapter before we do some problems. Theorem 73 says a secant angle whose vertex is inside the circle, here's the key, the inside the circle thing right here. A secant angle whose vertex is inside the circle is equal to, in measure, to half the sum of the arc intercepted by it and its vertical angle. So, this is just one of the secant angles that we're going to talk about, angle APB. Angle A, if you're trying to find the measure of angle APB, which is a secant angle, according to the definition of a secant angle, we can find the measure of this angle by adding this angle and this angle. That's the two angles two arcs that are intercepted. I meant to say arcs. The two arcs intersected by this secant angle and its vertical angle. You add these two up and you divide it by 2. So angle APB, if you want to find that, it's half the measure of AB plus CB. Got that? If we wanted to find this angle right here, so we wanted to find APC right here, we would say this angle equals half the measure of arc AC plus the measure of BD. So you add these two arcs together and divide by 2, and it will give you this one, and of course vertical angles are equal to this one. Now the second theorem has to do with a secant angle whose vertex is outside of a circle. So here we have, these are both secants because they intersect the circle in 2 points. That's the definition of a secant line. But this time it's going to intersect outside of the circle. So to find the measure of that angle, APD, or APD, whichever one you want to do, APD for some reason, if we want to find this angle right here, what we're going to do is we're going to take, well, let's read the theorem. So secant angle whose vertex is outside a circle is equal in measure to half the positive difference of its intercepted arc. So it's intercepting this arc right here and this arc right here. What it means is subtract the smaller one from the larger one and divide it by 2. So APB is equal to half the measure of AB minus, that's the difference, the measure of CD. So, if this one is 60 degrees and this one is 20 degrees, the arc, if we want to find the measure of APB, we would say it's 1/2 of 60 minus 20, and that would be 20, that would be 40, so it would be 20 degrees. These are pretty simple. All right, let's try a couple problems from your book. Okay, we're going to do 15 through 17 and then 19 through 23. So I'm basically doing all your homework. So pay attention. Okay, here we have a circle and they're giving us this arc. Let me just make sure that I can read this correctly. Yeah, they're giving us this arc right here, and they're giving us this arc right here. So the first thing I want to know is angle R. Well, what kind of angle is angle R? It's not a, we wouldn't call this a secant angle. We would call this, its vertex is on the circle. So we would call this one an inscribed angle. So if we're going to find the area of the measure of the angle of an inscribed angle, remember it's half of the intercepted arc. So angle R is going to be 15 degrees. You have to be able to recognize what kind of angle we're talking about. This one is on the center of the circle, so it's inscribed, so it's half of the arc. Let me just make sure I keep my answers close by. This is 15. Okay. Next one is we want angle F. Okay, look at angle F. It's 2 secants. The vertex is not on the circle. The vertex is outside of the circle. We have 2 secant lines. So remember, how do we do this? We take the 2 intercepted arcs. So here's our angle. It intercepts this arc and intercepts this arc. So we would say 90 minus 30. And that would be, we would divide it by 2. Take it times 1/2. So we get 1/2 times 60. So this one would be 30 degrees. So F would be 30 degrees. Okay. I'm still trying to find the answers. Okay. The next one, angle RLA. RLA. Okay, what kind of angle is that? All right, look, here's our vertex. It's right on the circle. So it's going to be half of the intercepted arc. So this one's going to be 45 degrees. These are pretty easy. 18. Why should angle RLA be equal to angle R and angle F? Well, what do you think? I know you're not even thinking right now. You're just waiting for me to give you the answer. This, I would say, is an exterior angle to this triangle. And exterior angles equal the sum of the remote interior angles. That's probably just one way to do it. Let's see, what does the book say? It's an F, that's it. Okay, maybe sneak that in there just for review, I guess. Okay, now let's look down here at this more complicated one. The one 15 through 17 was dealing with a secant angle that's outside of the circle. These are going to be inside of the circle. So number 19 says angle BNI. So here we go, BNI. These are 2 secants right here. They don't intersect in the center of the circle, they intersect somewhere else. So it's not a central angle. So they want BNI. So do you remember how to do these? We're going to add this arc, the intercepted arc, with this arc, and we're going to divide by 2. So this arc right here would be 35 plus 55. So if we add that up, we're going to get 90 degrees. We're adding both of these. Here's our arc, B and I, right here, our angle. So the intercepted arc would be this one, which would be 90, plus, here we go, here's our crisscrossing lines. Here's the other one, I think that says 40. And we're going to divide that by 2 and take it times 1/2. So we get 130 divided by 2, and we should get 65. So this one's 65 degrees. See how this works? We did this in Saxon Algebra too. Okay, angle TEG. TEG. Okay, same idea. Two secant lines, they intersect inside this circle, so we're going to add this arc plus this arc, and we're going to divide by 2. If we add that, I think that's a 55, so it's going to be 95 plus, here we go, crisscross, that would be that one, 35 times 1/2 would be divided by 2. And so for this one, we're going to get 65 degrees as well. And the big question on the table is, why should BNI equal TEG? Why should they equal each other? So, the reason for this is if two parallel lines are cut by a transversal, the alternate exterior angles are equal. So, if you notice these, I forgot to say this. Of course you wouldn't do this one. These two are parallel. So this angle, BNI right here, should equal TEG. So they are squeezing some review in here, because these are parallel lines and these are alternate interior angles. Okay, next one, B and H. Angle B and H. Okay, here we go. We have another pair of secants that are intersecting inside the circle. So you just do the same thing. I'm not going to waste your time. You're going to take this plus this divided by 2. And for 21, we should get the answer of, or 22, we should get the answer of 115 degrees. And then finally, why should TEG and BNH, trying to slow down, and BNH be equal to 180? And the reason for that is if two parallel lines are cut by a transversal, the interior angles on the same side of the transversal are supplementary. So that's just a little bit of review. Okay, let's quickly do one more proof, or one proof. I kind of did this one already so that I don't have to write so much in there. Let's see. I have an answer cover here. Okay, given FI, FI, LC are chords in the large circle. The measure of arc KR, we're supposed to prove that the measure of arc KR is greater than the measure of LI. This one's kind of hard because you have to think outside the box a little bit, and it's hard to know where to think to get what you're going to do. So see if you can follow along with what I did. First of all, we know we're going to write the given FI. I think I keep switching it from L to I. I think this should be an I. Whoops, my answer cover goes away when I write. Now I don't know what letter that's supposed to be. It should be I. So this should be I. FI and LC are chords. I can't read my own writing. It causes problems. Okay, everyone should be able to get the given. Even if you don't know how to go in these proofs at all, you should have something written down. You should copy the picture, you should write the given and prove, you should have your statements and reasons set up, and you should be able to write the given down. And then we can say angle KER, right here. This one right here. We can say, you can see how this point right here, there we go again, KER, see this point right here? That means it's an inscribed angle. KER is an inscribed angle. So we can say that KER is half of the measure of KR. Then we can say KER is also equal to, not only it's an inscribed angle in the small circle, but in the big circle, KER is a secant angle. So we can also say that KER is equal to half the measure of FC plus the measure of LI. So since we're dealing with two circles, there's two different things KER is equal to. So this angle is still going to be the same, whether it's a secant angle or whether it's an inscribed angle. So we can set, and the reason for this is the secant, that theorem about secant angles. If it's a secant angle, if it intersects inside the circle, then its angle is equal to the measure of the intersected arcs added together and divided by 2. Now, KER and KER are always going to be the same, so we can put what they're equal to each other. So we can say half of measure of arc KR is equal to half of the measure of the sum of the intersected arcs. And the reason for that is just substitution. So you write substitution there if I write my little finger away. Then we can say the measure of, if we multiply everything by 2, by multiplication, then we'd say the measure of KR equals the measure of, we lose the 1/2 is basically what we're saying. And then finally, the measure of arc KR is going to be greater than the measure of arc LI because the sum, let me just try to say this the right way, because the whole is greater than its parts. So we can write that down. We can say whole is greater than parts. I know that was painful to watch. So over here, this one would be substitution, and 5 would be multiplication. Okay, these are tricky. You have to think this is theorem 73. You just have to do a lot of thinking on these. That's all I can say. So, all right, that's it for lesson 5, and then tomorrow we'll be together for lesson 6 and 7 and review for the next test.